Okay, so what is a representative particle? A representative particle is the smallest piece of a substance. So it's a part that every other part is like. So if I pick up one of those, every other piece in that sample is going to look just like that. Okay? And for an element, the smallest piece is an atom, usually. But there's 8 of them that aren't atoms because they're diatomic, and when it's diatomic, it's a molecule. Cora. Okay. So that's why we could go straight from moles of Na to atoms of Na, is because Na is an element. So an element, the smallest piece is an atom. So that's 6.02 times 10 to the 23rd is about pieces. So you got to decide what kind of piece it is. It's an element, it's an atom, unless it's one of the 8 that's diatomic. Okay? For a molecular compound, the ones with prefixes, the ones with just nonmetals, it's going to be a molecule. And for an ionic compound, it's a formula unit. So these are the units that are going to follow 6.02 times 10 to the 23rd. It's either going to be atom, molecule, or formula unit, because that's what kind of piece it is. The dozen applies to whatever piece you've got there. Okay. So if I said a dozen sodium, that would be a dozen sodium atoms, because that's what kind of piece it is. So let's do a few of these to make sure we can decide which one it is. So representative particle of CaCl2 is, okay, what kind of piece does CaCl2? Well, is it an element? No, because it's got 2 capital letters. Okay, so we have to decide what that first capital letter is. That first capital letter is calcium, which is a metal. And since it's a metal, it's ionic, which makes that a formula unit. Okay. Representative particle of SCl2. Is it, first of all, you got to decide if it's an element or not. No, it's not. It's got capital letters, right? What kind of compound is it? Well, S is a non-metal. Cl is a non-metal, so that makes this molecular, which makes it a molecule. Okay. I don't know why that's there. Okay, the representative particle of carbon is? Is carbon an element? Is it diatomic? No, so it's an atom.
What happens when it's diatomic?
I wrote that down on the notes. And I wrote right on the screen, I added what it would be afterwards. Does oxygen have a charge? Every time you breathe, you get a little shock? No. Okay, so it's an element, okay, but it's two atoms stuck together, diatomic, and they're both nonmetals, so it's a molecule. It's non-metal atoms stuck together. All those ones that are going to be diatomic are all going to be nonmetals. Except, okay, that make sense? Okay, so that's how you pick which piece goes after 6.02 times 10 to the 23rd. Okay, we'd covered it before. I guess it just didn't stick well enough. Okay, so what our big topic is for the day is there's an issue with gases. Okay, and it's got to do with measuring them. If I got a mole of gases, how would I know? How would I know? Well, the only way we can measure things now to figure out if it's a mole or not is to weigh it. Okay? So, because lots of the chemicals we're going to deal with are gases. But picture yourself, okay, I said, here's a sample of helium. Weigh it and change those grams to moles. What would be the problem with that? Not just as gas, what would happen if you took that container full of helium and set it on the balance? Well, how about I could describe the container? A balloon. Well, what would happen to it? Float to the ceiling, does it weigh less than nothing? No, because, okay, it's less dense than the air. That's why it floats. It's got mass, but it's less dense than the air. But can you see why it causes us a problem? Gases are kind of hard to weigh. Gases are hard to weigh, but it's easy to figure out how much. It's easier to figure out how much space they take up. If I want to figure out how big a balloon is, all I got to do is fill up a sink with water and push the balloon down in it, and all the water that flows out was how much space the balloon took up. It's called measuring by the displacement method. How much water does it push out of the way? That's how much space it took up. Okay? So measuring volume is a lot easier for gases than measuring weight. Because to measure weight, what you have to do is you have to measure how hard that helium balloon is pulling up. And from that, you got to subtract the weight of the balloon. And you have to subtract how heavy the air would be that would be as big as that balloon. So it's a lot of math. It's not really measuring. Okay? So what we need is some connection between volume, which we can measure, and moles, which is going to be our tool for figuring out how much stuff is made. But there's a problem. If I pick up this remote and I weigh it here, and I climb to the top of the mountain and I weigh it there, is the weight of this remote going to change? No. Anybody ever taken a full bag of chips up to Big Bear? What happens to that full bag of chips? It gets bigger, at least, and sometimes it pops. Okay? That's because gases aren't constant the way mass is. That volume's not constant. That you can change the volume of a gas. I can't change the weight of this remote, but I can change the volume of the gas. Heck, think about how many balloons fit inside a tank of helium. Apparently the volume is changing from the inside of the tank to the outside of the tank, because the inside of the tank's at a higher pressure. Right? So two things affect the volume of a gas: temperature and pressure. So how do scientists deal with a situation where they want something constant, but two things can change it? The answer is, they make it so the two things that could change it don't change. They always measure at the same temperature and pressure. Because those are the two things that can affect the volume of a gas. If I don't change either one of those, then the volume should be the same. So when scientists pick something that everybody's going to agree on, they call it a standard. Standard means somebody picked it. Okay? So we're going to call it standard temperature and pressure. So they all picked the same room, okay? And what they picked was a room that had a cold. And the reason why they worked so hard to pick the room is because of Avogadro's hypothesis. This is way back when Dalton was coming up with the idea of the atom. Avogadro came up with this idea. He's the one who figured out that if you had the same temperature and pressure, you would have, if you had equal volumes of gas, they would have equal numbers of particles. That a liter of hydrogen and a liter of helium would have the same number of particles as a liter of oxygen. Doesn't matter what the gas is. In hydrogen, they'd be molecules because it's H2. In helium, they'd be atoms because it's just He. But it'd be that many pieces. Okay? That's why they named the number after him. Is because he saw that the number was the important piece, how many there were. Okay? Now, it's not called Avogadro's theory or Avogadro's law. It's called Avogadro's hypothesis because he was wrong about why. He thought that every molecule was exactly the same size. So that's not why. So it turns out there are equal numbers of pieces, but it's not for the reason he thought it was. So that's why he doesn't get the name. That's why it doesn't get the name theory or law attached to it. Is because the idea behind it was wrong. So it works, but not for the reason he thought it did. Okay? So the room they picked was one that was easy to recreate. Okay? They picked 0 degrees Celsius because that's easy to recreate. You don't even need a thermometer because that's the temperature that ice melts at. So if I fill a container full of water and dump ice into it, it'll keep cooling off for a while, and then that ice will stop melting. That's because the water and the ice got to the same temperature. And that temperature is going to be 0 degrees Celsius. So as long as you've got an ice water bath with chunks of ice sitting in it, you've made 0 degrees Celsius. Okay? So they didn't even need a thermometer to make that temperature. That's why they picked 0 degrees. And 1 atmosphere, that's about the pressure of the atmosphere on us right now. Okay. In Fahrenheit, it's 32 Fahrenheit, the freezing point of water. Okay. And for us, the pressure unit they use here is what, PSI? It's like 14.7 pounds per square inch is 1 atmosphere. Okay. We don't write out atmosphere all the time. Sometimes we abbreviate ATM for atmosphere. But we still need to give all the information. Now, that's just one. So they asked about what is that temperature in Fahrenheit. Okay, there's another temperature scale that's official for the metric system, and that's Kelvin. So 0 degrees Celsius is 273 Kelvin. And the official unit of pressure is called the Pascal. But pascals are really small, so they report them in kilopascals. Okay, so 1 atmosphere is that many kilopascals. We'll talk more about those later. Those of you doing series and sequences, it's the same Pascal. The guy from Pascal's triangle. Blaise Pascal. Not enough people named Blaise anymore. Okay, so we went all this. Okay, so what we've done all this for is we want to measure the volume of a gas, and equal volumes have equal number of pieces, and equal number of pieces are moles, right? So at standard temperature and pressure, if you're in that cold room, because 0 degrees Celsius is a cold room, if you're at standard temperature and pressure, if you're at STP, again, scientists are lazy. If you're at STP, 1 mole of gas is 22.4 liters. That's it. Every gas in that cold room, 1 mole will take up the same amount of space. Space of about 11 2-liter bottles. This is called the molar volume because it's the volume of a mole. So we can write this a little bit differently. I could write that 1 mole equals 22.4 liters. What can I do with things that say they're equal to each other? I can make conversion factors. So this is going to be just make a conversion factor like we've done for the past couple days, except now you can change mole to a third thing. Or you can change the third thing into moles. You can turn from liters to moles and from moles to liters. Okay. So the number next to moles is still going to be 1. Hopefully you've noticed that pattern doing the work for the past couple days, that if you wrote a mole, you wrote a 1 in front of it. Okay. And the liters, if in front of liters, you write 22.4. Just like in front of molecules, you write 6.02 times 10 to the 23rd. In front of grams, you actually have to do the math. So let's try a couple. What is the volume of 4.59 moles of CO2 at STP? So I've got 4.59 moles of CO2. What unit do I want to get rid of? Moles of CO2. Where's it got to go? On the bottom. What can I turn moles of CO2 into?
1 mole into 22.
Okay. The new one is I can turn it to liters of CO2. Yesterday we could have changed that moles into grams of CO2 using the periodic table, or we could have turned it into molecules of CO2 using 6.02 times 10 to the 23rd. Now we can turn it into liters. And 1 mole is 22.4 liters because we're at STP. And I've got the unit they asked for, so I'm done. Except for typing buttons. 4.59 times 22.4 is 103 liters of CO2. So you can see it's the same math. It's not new math, we just got a new number we can change to. That's why we like this math, is we don't have to learn new math every time there's a new problem. We do the same stuff to do all the problems. Hey, how many moles is 5.67 liters of O2? At STP. It's not at STP, we don't know what to do. So I start with the 8.8 grams of CH4.
I thought it's liter.
Oh, it's liters, isn't it? So if you copy the wrong unit, you'll get the wrong math.
And it's 5.67.
Well, what about, you know what, I'm looking at a different question. Let's start over. 5.67 liters of O2. And I want to get rid of Liters, where's it got to go? On the bottom. And liters I can only change into moles. And 1 mole is 22.4 liters. So now I've got the units they asked me for. So 5.67 divided by 22.4, because the 22.4 is on the bottom. And I get 0.253 moles of O2. Yeah.
So the only time we multiply is when the decimals on the top.
Whatever number's on top you multiply, and whatever number on the bottom you divide, and ones we don't type in, because technically I multiplied by 1, but that's again, scientists are lazy. I'm not pushing times 1. Okay. So we can go back and forth. That's how we can go back and forth between liters and moles, which means anything I can turn into moles, I can turn into liters. That make sense? Okay. Or anything I can turn liters into, anything I can turn moles into, I can turn liters into.
So we can turn liters into formulas?
Yep. Whoa, what happened there? That's not what I clicked on. Okay. So what's the volume of 8.8 grams of CH4 at STP? Okay. So what unit do I want to get rid of? Well, grams of CH4. It's got to go on the bottom. Can I turn grams of CH4 into liters? No. But I can turn grams of CH4 into moles of CH4. You did that a few times last night. I just need to add up the numbers on the periodic table. So 1 carbon is 12.01 grams. 4 hydrogens, 4 times 1.01, I can do that in my head, is 4.04 grams. So altogether it adds up to 16.05 grams for CH4. So this is just like we've been doing for the past couple of days. That's not new. Here's the new stuff. What do you want to get rid of? Moles of CH4. Where's it got to go? On the bottom. What can I turn moles of CH4 into? Can I turn moles into liters? Yeah, so I can put liters of CH4 on top. The number next to moles is still 1. The number next to CH4 is still 22.4. Sick kids. And divide by 1605. So I push 8.8, and the 1605 is on the bottom, so I'm going to push divided by 16.05. And the 22.4 is on top, so I'm going to push times 22.4. And that gets me 12.3 or 12, or somewhere in that range, liters of CH4. Hugely different than what you've done for the past 2 days? It's just, you can change to liters instead of molecules. You can change to liters instead of grams.
Why should we do that?
Because I can't measure how heavy a gas is.
But do we always have to do it now? It's like, for example,
Well, it depends on what the question asks.
okay, so like when it asks, yeah, okay.
Okay, so the question decides which conversion factors you use, right? The units you start with and the units you end with are your guide to getting there. Okay, so I gave you that diagram on the top of the table, but now we got to add to it. We got to add liters to it. Okay, so the central idea in this chapter is the mole. And the first thing we learned is that we could turn grams into moles using the numbers off the periodic table. That I can turn grams into moles. And then we said we could do molecules, but today we said we could do volume. That's 22.4 liters. Or we could do representative particles, and that was 6.02 times 10 to the 23rd. Now, some of those representative particles had pieces to them. A molecule has atoms. A formula unit has atoms and ions. So I could do one more step to turn it to atoms or ions by counting. So this right here was that long, was the thing all the way across the top of your page yesterday. Grams on one side, worked your way over until you got atoms by themselves. That make sense? So all we've added is this little branch over here. Okay? So with that, here we go. Oops. Okay, so here's what I need you to do is everything in a row needs to have the same value, so it'd be the same amount of stuff, just measured in a different unit. So, for example,